Hello, my amazing students. This is Mrs. A, and we are here with the last chapter, the last section in the last chapter in our class material. So we're doing 9.3, which is the hypothesis test for the difference in the mean of paired dependent data. Okay, so what we're going to have to do here is just a little bit different. We're not going to be able to do this from the stats. We're going to have to go straight to the data because the data is paired and we have to actually list one set of data, list the other set of the data, find the difference between the two, and then perform the one variable stats on that one and use that one for our t-test. So I'm going to show you some examples of how we're going to do that, and then we will be done. And all I'll have to do is put on your homework for the rest of the chapter, and we'll be done with videos, and you won't have to see my face anymore. But I hope you have found them helpful to really get understanding the material well. But I am not upset that this is my last section of covering new material with you. So here we go. Right, so this one is a little bit different. This section presents methods for testing hypotheses and constructing confidence intervals involving the mean of the differences of the values from two populations that are dependent in the sense that the data consist of matched pairs. So basically the only thing that is different here is that the pairs are matched up instead of the pairs being independent. Everything that we've done before were independent samples in the mean when we were finding the difference of the mean of independent samples. That was 9.2, and now 9.3 is a little different because we're actually matching up the pairs and doing the math with the original data and not with the stats. So basically some sort of something is matching this data together, some relationship such as before and after measurements from the same subjects or IQ scores of husbands and wives that belong to each other. Okay, so let's see how this plays out. Now this is good experimental design. When designing an experiment or planning an observational study, using dependent samples with matched pairs is generally better than using two independent samples. So it's a recommended method for doing experiments. So here we're talking about the objectives. What are we trying to do? We're trying to use differences from two dependent samples, matched pairs, to test a claim about a mean of the population of all such differences. For the confidence interval, again, this is not our focus. We're going to, again, use the differences of the two pairs. So the cool thing about this is we only have to do the prep work once, and then we use the t-test, and we'll use the t-int test, and we'll get it all done with only one prep here. So 3 conditions, again, requirements. Samples must be randomly selected. You've heard that before. Samples must be dependent instead of independent, because that's what we're working on here, paired samples. Both populations must be normally distributed. Either or both of these conditions must be satisfied. The numbers of pairs of sample data is large, or the pairs of values have differences that are from a population having a distribution that is approximately normal. So either the original population started out as normal, or we have sample sizes that are greater than 30. And again, the samples match because they're paired. If these requirements are met, then the sampling distribution for D bar is going to be approximated by a t distribution with n-1 degrees of freedom, where n is the number of data pairs. So once we get it paired off and subtracted, we're going to treat it just like we did on a hypothesis test in Chapter 8 when we only had one sample. We'll treat the difference of the two means as a single distribution. All right, so here we have N is the number of pairs of data, D is the difference between entries for a data pair, and the mean of D is the hypothesized mean of the differences of the paired data in the population. The D bar is the sum of all the individual D's divided by N, so the sum of all the differences divided by N, and the standard deviation of the differences. There's your formula, but again, we're going to use the T test that is given to us in our technology on our TI 8384. So here is the procedure. State the claim mathematically and verbally. Identify the null and alternative hypotheses. State your H-SVO, H-SVA. Specify your level of significance. Determine your degrees of freedom, which will be your N minus 1. Since they are paired, both samples have the same size N. Determine the critical value from your T distribution. And if your N is greater than 29, use the last row. And then determine the rejection region, which is going to be determined by your level of significance on your T chart. Then calculate your D bar and your standard deviation, which again, we will do that with the calculator. Find your standardized test score and make a decision to reject or fail to reject the null hypothesis. So interpret your decision. There's the confidence interval. Again, we would do that on the calculator using the T distribution. So again, verify, this is our procedure, verify that the sample data consist of dependent samples or matched pairs, and verify that the requirements in the preceding slides are satisfied. Find the difference D for each pair of sample values. Now, I'm going to do this on my calculator because it's less work. Find the value of D bar and S of D. For hypothesis test and confidence intervals, use the same t-test procedures used for a single population mean. So it's been a while. It does look like we're going to have to find these, but I think we're going to be able to find these using our one variable stats. So here we have data list ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages were matched according to the year that the awards were presented. This is a small random selection of the available data so that we can better illustrate the procedures of this section. Use the sample data with a 0.05 significance level to test the claim that for the population of ages of best actresses and best actors, the differences have a mean less than 0. Okay, so the differences have a mean less than 0. So here we have each individual. There's the actresses, there's 5, there's the actors. We're subtracting actress minus actor to get a negative 34, negative 9, negative 5, negative 9, and a 6. Okay, so now we're going to take those differences. Okay, they're doing the requirement check. The samples are dependent because the values are matched by the year in which the awards are given. The pairs of data are randomly selected. We will consider the data to be a simple random sample because the number of pairs of the data is 5, which is not large. We should check normality of the differences, and we should check for outliers. There are no outliers, and the normal quantile plot would show that the points approximate a straight line pattern. So we're going to assume normality. All right, so step 1, the claim that the differences have a mean less than 0 can be expressed as mu of D is less than 0. The original claim, if the original claim is not true, then we have mu of D is greater than or equal to 0. The null hypothesis must express equality, and the alternative cannot include equality, so the mu of D is greater than or equal to 0 is our alternative, no, this is our H sub O, excuse me, it's got the equality. This one is our H sub A, and this was our original claim. So the significance level is 0.05. We use the student T distribution. So before finding the value of the T statistic, we're going to find the values of D bar and S sub D. So the differences are -34, -9, -5, -9, 6. Okay, finding the D bar is just the mean of those. That's not too hard. And then the standard deviation. So let's go ahead and do that on our calculator. I'm going to do this much on the calculator. So we're going to go back to our original data, and I'm going to show you how to do this on the calculator so far. All right, so this is pretty simple. We're going to hit Stat Edit. Okay, when we do, notice that I have entered into L1 and L2 the values that they had down here. So let's go back to the value list here. And there's the value list. And I entered into L1, I entered all of these. And then into L2, I entered all of these. Now, when I went to this one right here, let's see if it shows it here. It doesn't show it anymore, it shows the values. But what I did here in L3 is I went up there and I hit L3 is equal to, and then I did second L1 minus second L2. So now, do you see this little defining statement I have down here? L3, and I'm doing this up at the very top. L3 is equal to L1 minus L2. So I'm making a column for my difference here. And then when I enter it, I get -34, -9, -5, -9, 6. -34, -9, -5, -9, 6. So this little sample, it's not too hard to just go ahead and do this by hand, but I'm showing you this so that you can do a little bit more complicated sample with your calculator. So now I need the differences. I need their mean and their standard deviation. So I'm going to do that with a one variable stats on L3. This is the column I'm going to work with. So I'm going to do stat and then calculate. And then I'm going to go to one variable stats, but when I hit enter, remember it's going to blink there. I'm going to say, where do you want me to get your stats from? And so I'm going to say L3, which means I hit the second button and I hit the 3 button and I get L3. So once I've told it to go to L3, I hit enter, and guess what it gives me? X bar is -10.2. My standard deviation is down here, 14.65. So let's go to the data here, and we were right here. Okay, so there were those values that I had in L3. And then when I run the one variable stats on L3, I get -10.2 and -10.2. I get standard deviation 14.7, standard deviation 14.65, which rounds to 14.7. So you can do the same thing. You're going to hit stat and then edit, and then you're going to put one of your data sets in L1, you're going to put one of your data sets in L2, and then in L3, you're going to put the difference between the two data sets. Okay, so then when you do all of the, do a one variable stats on L3, you have this D bar and this S sub D without any calculation work. So now it says use the T statistic, but I'm going to go ahead and do it. So you could have done it by hand, or you can go do the t-test. So let's use the data that we have and go do the t-test. So I'm going to do stat test, and I'm going to do the t-test, not the two samples. Right, so I am not using the two sample t-test now. I'm just using the t-test. I only have one item that I'm concerned with, and it's the difference of the two pieces of data in each case. So I'm going to use the t-test, and when I hit on the t-test and I hit enter, then I have a choice of doing data or stats. Well, I'm going to go ahead and look at this and notice that my X bar is negative 10.2. So they have translated this data from the other one into this one. I did not have to enter that. They already took the S of X from the data that I already have in there, and they put it in there. So it's already computed it for me. The only thing I have to watch out for is that this mu sub d is 0. Okay, so it says, using these sample statistics and the assumption from the null hypothesis that mu sub d is 0. Now, when I came in here the first time, that mu sub d was 7, probably from a previous calculation, and I had to change it to 0. But I didn't have to change the rest of the stuff. It came in with the data. So, and there's a less than that's already sitting here. And my data, when you go back to my hypothesis test, and you look at what our hypothesis was saying, the H sub A is less than. So I'm going to have the less than situation here. So I'm going to go back over here, and I'm going to click in the less than situation there. And everything else is ready, and it's ready for me to calculate. So I'm going to come down here, right there. I'm going to hit enter, and we'll see what happens. So I get negative 1.5565, which looks pretty close to negative 1.557 to me. And then, so I get my test statistic, which will be T, a t-test. Now I'm going to go to the next one, and guess what? It also gave me my p-value, 0.0973. Okay, so here's the p-value, 0.0973. And I have my test statistic and my p-value, and I am going to compare that with the 0.05. And 0.05 is this right here, 0.0. All right, so the p-value of 0.09 is greater than the alpha of 0.05. Remember, the rule is if the p-value is low, the null must go, but the p-value is higher than our 0.05, and so we're going to fail to reject the H sub O. Okay, we failed to reject because the test statistic does not fall into the critical region, and we conclude that there is not sufficient evidence to support that the mu of D is less than 0. There's not sufficient evidence to support the claim that for the population of ages of best actresses and best actors, the differences have a mean less than 0. There is not sufficient evidence to conclude that best actresses are generally younger than best actors. So they're just interpreting the results that they got there. But that process is what we're going to use for the other ones as well. So here we have another example. And again, we're going to use the data. We're going to subtract them on our calculator and put them in the third column here. So what I'm going to do is I'm going to go in and I'm going to enter into L1 and L2. And then I'm going to put the difference into L3. Okay, so I have entered my data in L1 and L2. I cleared out L3, and now L3 is going to be L1 minus L2. So we're going to do this in such a way I can make this difference go in any direction I want to. Basically, I want it to go the same way the example's going, so we're going to subtract them in the same direction they are subtracting them in. First, let's read the word problem. It says a shoe manufacturer claims that athletes can increase their vertical jump heights using the manufacturer's new strength shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the strength shoes for 8 months, their vertical jump heights are measured again. The vertical jump heights in inches for each athlete are shown in the table. Assuming the vertical jump heights are normally distributed, is there enough evidence to support the manufacturer's claim at alpha is equal to 0.10? Right? So when we look at this, we're going to say that we're going to do it in such a way that the mu of D is less than 0. So if the mu of D is the claim and they're supposed to be getting higher, then they're subtracting the first one minus the second one. So we're going to go ahead and do that same order. So here for L3, I'm going to say L1. So second 1 gives me my L1 minus my second 2 gives me my L2. And that's going to be the value that's going to go into L3. I hit enter and all of the values are calculated for me. So now I need to find my D bar and my standard deviation of the difference. So I'm going to do stat calc, and I'm going to do a one variable stat, but when I hit enter, I'm going to go to L3. So second 3 gives me L3, and I get my X bar is negative 1.75. So hopefully they got the same thing. They did their subtraction here. They went ahead and figured out their standard deviation using their D squared. I did my standard deviation using my one variable stats. So I get negative 1.75. They got negative 1.75. And 2.1213. And I got 2.1213. I think my way's better. I like using the one variable stats. It's faster. So I get the same thing that they do. And now I'm going to go ahead and I have everything calculated. I'm going to go ahead and do my T distribution. So I'm gonna go just like this, not touching anything, and I'm gonna go stat test t-test, and I'm gonna hit enter, and let's see what happens. Look at that. Because my data is in there, it gives me the X bar, it gives me the standard deviation. I don't have to do anything. Now remember, we're saying that it's going to end up having a negative. The difference from L1 to L2 should be negative because the L2 is bigger. Okay, that's the claim. But we always assume that the mu of D is 0, even though we're doing left-tailed tests. So we get negative 1, we get 2 minus 2, and then we go back and we look at the claim was mu of D is less than, so we're going to use our less than right there. So we're ready to calculate our T statistic. Let's get down there and hit calculate, enter, and we get negative 2.33. Our p-value is 0.026, and then it gives us our stats again. So let's go over here, our test statistic. We calculated negative 2.33. They did it by hand. They calculated negative 2.33. I like the technology, don't you? All right, they did not calculate the p-value, but we're going to do it with the p-value too, just to show that it is correct. So the cool thing about it is when we use the technology, we don't have to worry about the p-value. We just take it for what it is, because it knows when to double it and when not to, and this one wouldn't double it anyway. So our T is negative 2.33, degree of freedom 7, alpha 10. So aren't we going to go to our T table? And in our T table, we're going to find out what is our critical value. And our critical value, according to this, should be negative 1.415. But let's check that out with our T table, which is right here. Let me move this back a little bit. So here's our T table. And we're going to 7 degrees of freedom. So there's our 7 right there going across. And we're doing 10 in a left tail. So we're doing one tail 10. So 10 in one tail is right there, the last column. So let's take 7 and go all the way across the last column. And lo and behold, let me get it closer. We get 1.415, which is the same thing that they said right there, 1.415. Okay, so you're going to get your critical value from your T-score chart. You're going to get your test statistic from your t-test. And everything is pretty simple. So if we look at this, we've got our critical value, negative 1.415. We've got our region of rejection region there. We got negative 2.33 as our test statistic. It is in the blue area. It is rejected. So we must reject our null hypothesis. And the null hypothesis was not the claim. So since we reject the null hypothesis, it looks like the claim is good. So we put the next one down here at the 10% significance level. There is enough evidence to support the shoe manufacturer's claim that athletes can increase their vertical jump heights using the new strength shoes. So that's pretty cool. One more example. Okay, a medical researcher wants to determine whether a drug changes the body's temperature. 7 test subjects are randomly selected and the body's temperature in degrees Fahrenheit of each is measured. The subjects are then given a drug, and after 20 minutes, the body temperature of each is measured again. The results are listed below. An alpha 0.05. Is there enough evidence to conclude that the drug changes the body's temperature? Assume the body's temperatures are normally distributed. Now notice it does not say it raises or lowers. It just says it changes the body's temperature. Okay, so what we're going to do is set an equal to and a not equal to as our 2 options here, because it doesn't say raise or lower. It just says equal or not equal to. So now we're going to put these values into our stat and edit. Okay, we're going to enter in to our L1. Got to go over here and clear out all of these old things here. Got to get back over to L1 and clear it out. So clear and enter. That gets rid of old data. And go to L2. And I'm going to clear and enter. And I'm going to go to L3. And I'm going to clear and enter just to get rid of all that old data. And now on L1, I'm going to go ahead and go down below to the first one. And I'm going to enter each one of these. And then I'll come back to you in a moment. Okay, so I've entered in my L1, my L2, and my L3 as the difference between them. So I've gotten those all calculated out. And now I'm going to go to my one variable stat. So I'm going to hit stat and calculate and one variable stat. But instead of hitting it again and doing L1, I'm going to do second 3 to do L3. And then when I do my one variable stat, I get X bar is 0.557. And the standard deviation of that is going to be 0.9235. So let's go over here to our screen and click down and look and see if we got the same thing that they did. So we had our X bar, our D bar, 0.5571 and 0.5571 there. Our standard deviation of the D is 0.9235, and right there it's 0.9235 right there on that fourth column there. So I got those, and now I'm ready to go ahead and do my t-test. Now, before we do that, let's go back and look and see what they've done. We haven't done our t-test yet, but they can do a little bit of work beforehand. So basically, we're doing 0.05. They talked about the H sub O and the H sub A, not equal to. I didn't have that symbol, so I just said not equal to. And that's just a restatement of the problem there. And then on this one, they gave us our level of significance. Our degree of freedom is 6, because remember, our number of samples here was 7. And so 7 take away 1 is our degree of freedom 6. And again, that's just a restatement of our problem. So now we're looking for these critical values. And these critical values are going to be, since we have a not equal to situation for our alternative hypothesis there, not equal to, we're going to have a split tail, which means we have 2 tails and we've got 5% in 2 tails. So let's look at our T chart again and look at here, 2 tails and 5%. So we're coming right down the middle. We're going to a degree of freedom of 6. We get 2.447. Okay, so it's in 2 tails, so it's going to be 2.447 and negative 2.447, which is exactly what we have here on our slide. Okay, so we know how they got that. We know how they got this and this from our data. And so now we're going to use our T test to get that test statistic here. So let's do that. So here was our one variable stats. So now, since we're done with the one variable stats, we're going to go here and do our stat and our go over to test. And we're going to go down just one and do a T test and hit enter. And now, guess what? All of my data is there. That is my X bar. That is my standard deviation. My N is 7. My mu of D is listed as 0. And this is the problem right here. My last one was less than. I've got to change that to not equal to. So that's the only thing I have to change on here. I don't have to enter anything except that. So I'm going to hit enter and change it to not equal to because of the null hypothesis. We go 1 down. I'm going to calculate. And I get T as 1.596, which is just what they get. And then we have the p-value is 0.16156, which I don't see the p-value on this one. So let's just use our test statistic. It lies outside the region because what? We go all the way with negative 2.44 and positive 2.44, and 1.596 is not in the rejection region. Therefore, we will fail to reject. And since this is a two-tailed test, we're going to say the 0.05 is split with 2 tails of 0.025. And the p, where's my p-value? Oh, p-value is right here. Sorry about that. P-value is not on the screen. So the p-value is 0.1615, and 0.1615 is definitely greater than the 0.025, and we will fail to reject. Okay, so we just did not list the p-value here, but we have it on this calculator screen right there, and it is definitely bigger, and therefore we do not reject. We fail to reject our null hypothesis. There is not enough evidence at the 5% level of significance to support the claim that the drug changes the body's temperature. So, alternative method used when population is not normal and N is less than or equal to 30. Basically, they're talking about that bootstrap again, which is outside the purview of this class. We will not deal with this. So now, hopefully you get the big picture. How do you determine if you can use either test? Know your requirements for each one of these tests. When do you use the Z-test? When do you use the T-test? Make sure you know that. Make sure on your 4x6 cards you have that noted. Now, remember on your test, you will have the little sheet for the formulas, which basically is going to help you out a lot. But let's just look at this section and see what they have on there. Okay, so let's look at our section, which is chapter 9. And chapter 9 here, they basically have a lot of formulas that have been crossed out, but we will do some of that. Okay, now we're going to be using our technology, and they're not showing you when to use the T and when to use the Z on here. So I would have that on my 4x6 card. When do you use which test? I would definitely go ahead, and you should have one of these in your book. So I would look at this and see what's on there, because this is the one you're going to get. And then I would go ahead and make sure I had whatever I needed to know for sure which test to use on my 4x6 card. How to choose and execute the correct calculator test, when to pool, when not to pool, and how to interpret your results. So here are your 3 homework problems. You have 3 homework problems for this whole chapter. 9.1, 9.2, 9.3. That's it. 3 book problems for the whole chapter. This is an extra credit assignment that involves replacing 3 bad assignments earlier or just getting a higher overall grade. Win-win. Please remember that all of the online work is ready for you, and there is no late acceptance this time, as the course will be over on the day of final exams. Thus ends chapter 9, and thus ends all of the new material that I have to teach you. I know you're excited. So I will come back to you probably tomorrow with the answers to chapter 7. The next day I'll give you the answers to the homework on chapter 8, and then the homework on chapter 9 according to the schedule that I gave you. I will provide you with a practice test for the final exam. We will spend most of Tuesday diligently working through that practice final. And this is Mrs. A, and may God bless your day.